Thank you. So I'm going to show a part of the research that I did during my PhD, which I completed last December, working with my advisor, Professor Mohamed Skandarani, and with collaborations with Professor Tamai and Dr. Carlisle Tucker. So I'm going to first talk a little bit about the background of this work, which started with the Deepwater Horizon blowout, which everybody is very familiar with, when almost 5 million barrels of crude oil was released in the northern Gulf of Mexico. And oil forecasts were extremely challenging. And one of the main reasons is the wide range of processes in the acting in that area and in the Gulf of Mexico. So in oil leak, images of the oil leak highlighted the influence of, you can see from different patterns of flows. Here you can see even from influence of mesoscale features to submesoscale features, and then even smaller scales acting on the transport of oil. So my work is related to CARTH, which was a consortium that was formed by several researchers from several institutions to work with the goal of improving our ability to forecast the oil spill in the environment. And in 2016, this consortium conducted a massive experiment in the area of the oil spill, the surrounding areas, which was called the Gaussian Submesoscale experiment. So the mission was to understand these processes near the DeSoto Canyon, where the spill occurred, and how those processes affect the transport of pollutants. And this experiment was centered in the release of over 1,000 surface drifters on that area. And my work, our goal is to extract information about the submesoscales from these surface drifters. Just talk briefly about what are these submesoscale features that we are looking for. So they are mixed layer processes with horizontal scales on the order from 100 meters to about 10 kilometers, and time scales in the order of hours. These processes, they occur in the mixed layer, as I mentioned, in areas where you have intense horizontal density gradients, and because they are relatively small scale and they evolve very fast, they are hard to sample, they are hard to observe. And because of that, the observations of submesoscales are still rare, and most of the knowledge that we have from them comes from numerical models and designed with idealized numerical simulations. As you see here, an example of this image here is the convergence, horizontal convergence, normalized by the planetary vorticity from a round simulation with a 500 meters resolution. And you can see here a strong convergence area, which is indicative of strong vertical velocities in the mixed layer, which is believed to affect transport and mixing. So the flow regime in at these scales, they are only partially constrained by geostrophy and the hydrostatic balance. So you would expect velocity gradients on the order of the planetary vorticity. Here you see reaching up to almost 5 times the planetary vorticity. And one way people identify these processes is releasing Lagrangian drifters, surface drifters, and estimating the kinematic quantities from clusters of drifters from the change of shape. If you have 3 drifters, you have a triangle, and you see how the shape of this triangle evolves, and you get an estimate of convergence, relative vorticity, and rate of deformation. And what I want to do here, I want to reconstruct the submesoscale velocity field in an Eulerian frame and compute these quantities from the Eulerian field by finite differences, and see if we can observe we can map these features. So two things that I'm going to show is that we mapped differential kinematic properties under submesoscale activity, and we used a technique that I'm going to talk about later called Gaussian process regression, in which we optimize correlation scales in space and time. And I'm going to characterize this regime also in terms of these correlation scales. This work will I'm going to present two parts. The first one, where I have a large amount of observations in a very small area. So I have a very high resolution observations during a 12 hours period, and I reconstruct the velocity field over that area. This work was recently published on the Journal of Physical Oceanography. And the second part, I'm going to focus on advanced technique I used to map more complicated features when you have such strong convergences that drifters align over these convergences and we lose spatial coverage. So I'm going to show a way of overcome this type of difficulty. The Lagrangian submesoscale experiment, which was conducted by Karth, which I'm going to refer as LASER. So as I said, released over 1,000 drifters in the DeSoto Canyon. And the surface drifters had a sampling interval of 15 minutes. And the observations that I'm actually going to use in the reconstruction of the velocities are the velocities estimated from the displacement of these drifters. Here you see a map of temperature measured by an airplane, and these measurements were taken about 6 hours before the release of these drifters. And these drifters in the stars here are the initial position of each drifter. So you see a very concentrated release of drifters. You see they are occupying an area of roughly 20 kilometers by 20 kilometers. And from the temperature, you can see several submesoscale features. You see a front here. And this area, the cold temperature indicates lighter waters because it's coastal waters and the density is controlled by salinity. So the cold water is actually colder and fresher water. So the density front here, you have lighter water and warmer water this side. And these dots are ship measurements of temperature. This was about 1 day after the image. So you see it's not the temperatures from the dots are not exactly matching the aircraft measurements, and that's part of the fast evolution of these features. And the vectors here are wind measurements from the ship. So to start part one, I selected those 340 drifters that I showed that were released over you can see it's a cyclonic eddy here. So there is a cyclone. This is an image of satellite. So these drifters, they remain inside that eddy for about 40 hours. where they, so they sample the flow field at several separation scales. Here, this image, I have the evolution of histograms of pair separations. So in the beginning after the last drifter deployment, you'd have drifters apart from a few meters to 15 kilometers, while and here in most of them is inside a mode of about 5 kilometers. So this red color is the mode of the distribution of pair separations, and this is the evolution in time during these 40 hours, roughly 40 hours, where they stayed clustered. After this, the black line is the mode. So after about 40 hours, there was a storm that disrupted the drifters, and then that's why you see this noisy behavior of the mode, and you see the higher spread. I selected to analyze the first 12 hours because there is an abrupt shift on the mode separation. And after this shift, which happened from around 6 hours to 12 hours, they all became very stable. So here I have very high resolution observations, and suddenly there's something happening, and they stay stable inside the cyclone. And here I have drifters positions with the velocity of displacement and those temperature measurements that from the ship that I showed before. So here is after 2 hours after deployment, here is 5 hours after deployment, and here you have 12 hours after deployment. That shift in mode separation happened from here to here. Here, and you can see there is an alignment of drifters here, which gets tighter, and after it's broken. So this is probably the process that that triggered that change in the mode of separations. And in the area where the drifters were clustering, there is a strong density front. Here you can see from the temperature, but I have the profiles from the same sections. You have the profiles of density, and the drifters here are aligned around, that's 12, so they're around here. The vertical profile, you see the intense density front from near surface to between 40 and 60 meters depth, and here you have this the density front around x equals 8. So you have the density front around here. So there is an evidence of intense submesoscale activity happening there. The technique I'm going to use to map the velocity field into an Eulerian frame is called Gaussian process regression, which I want to estimate a scalar, which is designed by F, which is going to represent the quantity we want to estimate, which will be either components of the velocity. And F is a function of x, which is the position in space and time. And it is assumed that a number of samples of this quantity have a joint Gaussian distribution. So I have a prior mean and a prior covariance function. And conditioning this prior distribution on the observations that we have, we obtained a posterior mean, which is our reconstruction, our velocity reconstruction. And we have a posterior covariance, which provides error estimate for our posterior mean. Here in this equation, you see big K is the matrix of covariances, which are drawn from our covariance function. So here you have covariance between the points x, where we want to estimate the velocity, and the position of the observations. And this is the covariance of the observations with themselves, but it's also drawn with from the same covariance. And you have, you have a noise, observation noise term. In the setup for the laser data, I consider both velocity components to be independent, and the covariance function which I use to build the covariance matrices are three-dimensional squared exponential function. So here I have correlations in time, in the meridional direction, and in the zonal direction. And I'm considering two scales per each dimension. So I'm going to have two scales in time, two scales in y, and two scales in x. And I have the variance of, and the covariance also has a variance, which we have to estimate. This is just one sample, like how it works. I have observations in red, and the vectors are the reconstructed velocities. In these quantities, the correlation scales in time and in the horizontal direction, the variance and the noise variance, they are obtained by an optimization procedure, which is based on conditioning these parameters into the observations, into the drifters observations that we have. So we maximize the log marginal likelihood, we maximize this function, and by this we obtain our parameters. So after I optimize the parameters, I have the following results for the optimization detected an observation noise of about 1 centimeter per second in both velocity components, and a variance, and the optimization was able to identify two distinct scales on the observations: a dominant large scale with time correlations around 3 hours, and meridional correlations from 1.8 in the U component to 3.5 on the V component, and correlations in the X direction about 2.5 kilometers to 1.4 kilometers. And on a smaller scale with weaker variance, with time correlations of about 39 minutes, and horizontal correlation scales on the order of 400 meters. So just to illustrate the effect of each scale on my reconstructed velocity field, I reconstructed the velocity using only the larger scale, only the smaller scale, and both combined. So here I have an image of the horizontal divergence with the velocity vectors. Blue indicate convergence, and you can see that the larger scale gets the broader cyclonic pattern of the eddy, while the smaller scale captures strong velocity gradients. And combine them both, I obtained a smoother eddy, but with sharp velocity gradients inside. To verify, I did some error verification for my estimates. So after I have the covariance function optimized, I got about 50% of my observations I separated as training points, and the other 50 I separated as verification points. So I used the training points to estimate the velocities at the test at the verification points, and then I compute the errors at the verification points. So I obtained that 90% of the absolute error was below 2 centimeters per second, which was pretty small, indicating a good estimate. And 80% of, and here is the error normalized by the observed value. So 80% of the errors was less than 1/10 of the observed value. So you can roughly say that 80% of the estimates have a 10% error. And I also compared this error with the error estimated from the posterior covariance. So I subtracted the estimated error from the posterior covariance to see how good would be the posterior covariance to bound our analysis. And the posterior covariance overestimate the error, actually. So I have in about 1 centimeter per second, which is roughly the observation noise that was captured in the optimization procedure. So I'm going to show the reconstruction of the velocity field during this period. I'm going to show the velocities over maps of speed, relative vorticity, divergence, and rate of strain. You can see the magenta vectors are observations used, and this is an area of very low speed, and you see the cyclonic circulation, the drifters aligning, and then they break the alignment here. And this feature on the relative vorticity, you can see red as a strong cyclonic vorticity reaching 10 times the planetary vorticity. And you see as the drifters align, that relative vorticity intensifies. And once it breaks, you see a little spot with very intense relative vorticity. And the same feature is observable on the map of horizontal divergence. You can see a very strong convergence on where the drifters are aligned, and also very strong strain rate, which is indicative of frontogenesis, submesoscale frontogenesis process occurring. This type of observation is, this type of maps you'd see only before in numerical models, and you assume that this could happen. And here we can show them just reconstructing the velocity from these drifters. And actually the values that we found were slightly higher than what I've seen reported from numerical models, which would go up to 5 times the planetary vorticity. And here I have peaks of horizontal convergence to about 8 times the planetary vorticity. And so very strong submesoscales happening in the flow field. So to summarize this part, the Gaussian process regression was applied to generate high-resolution velocity maps from a dense array of drifters. Correlation scales and signal-to-noise ratio were determined from drifter observations through the Bayesian optimization procedure. The reconstructed velocity exhibited horizontal length scales from the order of 400 meters to 3.5 kilometers, and time scales from 40 minutes to about 3 hours. And our results presented the time evolution of vigorous submesoscale features displaying significant HS traffic circulation over an observed density front. So the second part, to motivate what led to the second part, that very often the surface drifters, they align over this convergence zone, they form a line and reducing the spatial coverage. And once you have drifters in a string of line, it's impossible to have estimate of convergence. And you can show here what happened in. This is a subset of about 100 drifters from that I used in the previous analysis. So this is several days that this cluster got separated. And here you can see. And once I tried to apply that same methodology directly on these observations, the results are not they're not good. I didn't see. I would expect that the line of drifters to be over a convergence line, and this didn't happen. And and these features here are not consistent with what we are seeing. And I identified a few problems that why this is happening. The first is the limitation of a stationary covariance function, which means that my correlation scales, they don't vary in time or in space. They are constant everywhere. They have the same correlations. So you have a feature that has a curvature, which is going to induce correlations in both directions. At this part, I would expect the correlations to be stronger along the alignment and smaller in the across the lines. But if you optimize the velocity scales, you're going to have in a Cartesian coordinate system, you're going to have correlations in both directions. And there is also the influence of larger flow fields acting on the drifters. So if you have the whole feature there displacing with a mean flow, that's going to induce correlations on the direction of the displacement of the mean flow. And that's going to affect the outcome of the optimization. So the objective of this part is to elaborate a framework to reconstruct the velocity field over a submesoscale from these observations. And there is also another aspect of this. There are different regimes here. You see a convergence area here, and here is more rotation dominated. So there are two different regimes on this flow field, which makes it even harder for a stationary covariance function to do a good job. The approach I'm going to present is the following. So this, in A, you have my raw observations. Blue dots are initial position of the drifters, and the red dots are the final position. Here is 3 hours. I just selected 3 hours period. So in the first step, I'll remove the center of mass at each time of the position of the drifters, and this is to remove the effect of the displacement of a mean flow. So from A to B, you can see clearly now the eddy, and you can see the convergence line considering all observations. The second part is that I'm going to select the drifters over the feature, the flow regime that I want to reconstruct, which here is what I believe is a frontal feature. Is the area with high convergence where the drifters are forming a line. So I'm going to select the red dots here, and from these red dots, I'm going to adjust a curve. This is the green line here is a polynomial fit, is a second order polynomial fit. I'm just a curve over this curvature. And for each observation, I'm going to define a new coordinate system where x direction is the shortest distance from the observation to the curve, and the y is the length of the curve from a predetermined origin to the nearest observation over the curve. So I'm basically turning x into cross front direction and y into a long front direction. And I will rotate the velocity components accordingly so that v is the along front velocity and u is cross front velocity. I'm going to evaluate this coordinate system adjustment by comparing to regressions using a regular Cartesian coordinate system. So first here, C1 and V are estimates using the adjustment, my new coordinate system. MV here is just because it's to separate, because in this case I'm going to use the same covariance function for both U and V, so they're going to have exactly the same correlation scales. C2 is the Cartesian coordinate system with the center of mass removed, so I'm just removing the effect of the mean drift of the mean flow. And C3 is just the original coordinate system. I'm going to check each different coordinate system with 14 types of covariance functions to verify if what makes a greater impact, if the type of covariance function that I'm using or the coordinate system adjustment. Here I selected 4 types of coordinate system, the squared exponential that I used in the first part, 2 classes of Matern functions, and 1 rational quadratic. And I combined them, adding them together. So here I have covariance functions which are 1 the squared exponential times a rational quadratic, and so on. I have 14 combinations of them. In the evaluation, I have 3 different sets of test points and training points to see if the difference that makes it is consistent, if it's not made out of luck. So in the first set, the black, in this figures shows the black dot are the training points, which are the points I'm going to use to estimate the velocities. And the red dots are test points. So I'm estimating velocity at the red dots using the black dots. In the first scenario, I have half of the observations for training and half for verification. In the second scenario, I have 1/12 for training and the rest for verifying. And the last one, I'm using the upstream observations for training, in the downstream for verifying. So I want to check the ability of extrapolating the results. I just have observations here, and I want to see how they perform here. And the comparison is done by estimating the error at verification points. So I have the estimate of each component minus the observed values, and I add them together. So I can compare, because the velocities are rotated, I add them, so I have an error that combines the overall velocities. I'm just going to show B and C, because A is the results are close to what I found in B. So I'm just going to show here the case where 1/12 of the data was used for training. Here I have block plots of the errors. The colors are the different coordinate systems, and each column here is a covariance function. And here I have the median of those errors. I used the median because there is a high skewness or high skewness on the distributions of errors. The new coordinate systems are blue and orange, and the Cartesian coordinate systems are green and red. And the adjustment the new coordinate system presented consistently better results in almost all of the covariance functions tested when compared to the Cartesian coordinate system. Okay, so so here the better results I found using the rational quadratic function and also the combination of different covariance functions. But still you can see the orange and blue they have smaller medians and smaller spread of the errors. And here's the test for the extrapolation case. So the errors were expected to be way bigger. And again, you see the adjustment of the coordinate system having a much better performance than the Cartesian coordinate system, especially for the same function, the rational quadratic. But again, in all of the covariance functions, they have a better performance. And the choice of coordinate system was more important for this case than the type of covariance functions that we used. So the results just to compare the results for maps of differential kinematic quantities, I'm just showing here the convergence at one time step using the different types of covariance functions, different types of coordinate system. So the two on top are using the curvilinear coordinate system, and the two on the bottom are using Cartesian coordinate system. The black line indicates the line where of 5 centimeters per second error from the posterior covariance function. So I'll trust the results that are inside that line. And you can see that the green vectors are the observations, and you see that the convergence line follows the alignment of the drifters, which does not happen quite well in the Cartesian coordinate system. On the other hand, the intensity of the convergence zone is similar in all cases, reaching almost 15 times the planetary vorticity. So I'm going to show the evolution of these kinematic maps during the 3 hours for the reconstructions using our coordinate system adjustment. So here's convergence. You can see a very strong convergence. The yellow dots are the drifters' positions. So you see that as the convergence line is transported by the background flow, so there's a eastward transport, and the drifters are aligned over this strong convergence zone, and which is also has a very intense relative vorticity. So these values are now even higher than the ones I obtained before. Very strong features, and this is just the animation for the strain rate. So very strong deformation. Summarize the second part. I presented an approach to reconstruct the velocity field over a submesoscale front. And the strategy they adopted helped mitigate the limitations of stationary covariance functions. The approach consistently reduced the estimate errors at verification points, and the velocity reconstructions were more sensitive to the type of coordinate system than the covariance function. The maps of differential kinematic quantities presented narrow and elongated features following the drifters, which are also consistent with submesoscale fronts. The next step of this research would be to implement non-stationary covariances to make the covariances to vary in space and in time. So one thing that I would propose would be to have covariance functions for different types of flow regime to be trained in a similar fashion as the approach that I just proposed. And I just put a sample of that here. I have maps of divergence, relative vorticity, and lateral strain rate. I have two different regimes combined here. I used two clusters of drifters. One is the ones aligned with the front, and the others are the ones in the strong rotation part. So at first I estimated the whole velocity over the whole area using just the estimates of the drifters aligned. And then I did the same thing just for the other drifters, and I weighted some using posterior covariances. I used the posterior covariances of these estimates to estimate weights, and with the summed weights, I was able to obtain different flow regimes, which you can see here. There is the alignment on the convergence zone, and the other ones are more rotation controlled. So the one thing that happened, the shortcoming that I have, is that the features are smoothed out because of the average of the two estimates. So this is also suggestions for research on this type of analysis. In a potential application, these applications, they don't have necessarily to be with drifters to estimate submesoscale. They can be applied to the Gaussian process regression can be applied to analyze different types of data, and the optimization procedure can be used to characterize other types of flow fields. And one thing that I'm starting to work with is that I'm applying the covariance functions, the optimization procedure, to try to estimate a background covariance matrix for optimal interpolation. That's something that I'm just starting, and that I'll see if it's possible. But I think it has merit, and it's something that can be done. And another application is to use the Gaussian process regression to reconstruct the uncertain response surface of an ensemble forecast. It's kind of a complicated name, but it means if you have an ensemble of model forecasts, and which are generated by a perturbation of a few specific parameters, you can obtain that function relation between the uncertain space of your model forecast and your forecast, and you can use that to estimate the uncertainty of this forecast, and also to estimate the background covariance function. So thank you.